Now, in our second video of looking at combining probability distributions, we're going to look at conditional probability, which is one of the really powerful and also really interesting areas of looking at probability generally. Probability is an area where you can start to study and you think, oh, that's obvious, yes, that's just common sense. And suddenly you go, what? Where did that come from? I did not see that coming and wouldn't have intuitively thought that was the case. And this is where it becomes really particularly fascinating. So to understand this, you're going to need to know about fractions and percentages. You're going to need to know some basic information about probability distributions. You're going to need to know about marginal and joint distributions, which we covered in the previous video. And this is where we got up to. We looked at this table which shows the marginal distributions of whether students enjoyed mathematics at school and the marginal distribution of their reasons for studying statistics and the joint distribution combining those two. And now what we're going to think about is, instead of looking at all students studying statistics and coming up with those probabilities, we said, well, let's just look at students who wanted to study statistics. That's the total number of the population we're going to consider. And this is where what's important to remember is that a probability is not a raw number. It is a fraction. It is a percentage, and it has to be a fraction of something. So if we're looking at all of the students who wanted to study statistics, then in terms of probability, 100% of our options are going to be students who wanted to study statistics. And what we want to know is, of that 100%, what percentage enjoyed mathematics and what percentage didn't enjoy mathematics. And it's not going to be 4% of 100%. It's going to be 40% of 100%, and it's who did enjoy mathematics, and it's going to be 60% of 100% who didn't enjoy mathematics. So that's what we call a conditional probability. We say we condition on whether they wanted to study statistics or not. Now, similarly, if we were to only look at the students who enjoyed mathematics, and now the 40% of students who wanted to study mathematics, that's the 100% we're looking at. So 4% as a fraction of 40% is 10%. It's actually 10% of that 100% who wanted to study statistics. And it's 90%, that's 36 over 40, is the same as 90%. 90% of those people who enjoyed mathematics had to study statistics for another course. So now when we look at that, what we can see is that in the top left-hand corner, we now have three different probabilities. Because what's changed is the thing to remember is that a probability, again, is a fraction. It's not a raw number, and it's the denominator is changing. The denominator is driven by what our condition is. So when we condition on wanting to study statistics, we say that 40% of students enjoy mathematics. When we condition on enjoying mathematics, we say 10% of students want to study mathematics and want to study statistics. And when we don't have those conditions, it's 4% of students. So what we say in statistics is that the probability of A given B is not the probability of B given A. So for example, the probability of enjoying mathematics given that you wanted to study statistics is not the same as the probability of wanting to study statistics given that you enjoyed mathematics. And this can have some profound real-world implications. Imagine, for example, that you're going to see your doctor and they do some routine blood tests and you test positive for a disease, which obviously causes you some concern. So you say to your doctor, how good is the test? And the doctor said it's a very good test. It's 99% sensitive. And what that means is that if you actually do have the disease, there's a 99% chance that it'll say you will, and only a 1% chance that it'll miss out the fact that you do. And it's also 95% specific, which is a way of saying if you don't have the disease, there's a 95% chance that the test will say you don't have the disease, and only a 5% chance that it will say you will. There's a 5% chance of a false positive. And so you say, well, is this a very common disease? And the doctor says, oh, yes, it's an extremely common disease. 1 in 50 people actually have this. That's 2% of people. And at this stage, your intuition tells you that that means it's almost certain, good test like that, common disease like this, it's almost certain that I have the disease, but because you've studied some probability, some statistics, you go, I'm going to think about this as a conditional probability. I'm going to draw up a tree chart just to make sure of my reasoning in this. So you start thinking about all of the people in your age group and go, okay, what the doctor's saying is that 98% of people don't have the disease, 2% of people do. Of those people who don't have the disease, 5% of them will test positive, even though they don't have the disease. There's going to be that 5% false positive rate of people who don't have the disease. And we multiply that out using the multiplication rule. So it's 5% of the 98% of people. Of all people going for the test, it's going to be 4.9% of people are going to have a false positive. They're going to test positive when they don't have the disease. Of people who don't have the disease, 95% of people aren't going to test positive. They're going to test negative while they don't have the disease. We'll multiply that out. 95% times 98% is 93.1%. So that's people who don't have the disease. Of people who do have the disease, the 2% who do, 99% of those, the test is going to be positive and show that they have the disease. Multiplying that out, 2% of 99% is 1.98%. And 1% of the people who do have the disease will be missed out. They'll test negative even though they've got the disease, and that's 1% times 2% is 0.02%. So we've covered all of the people there. We've got 100% coverage there, and we can see what the probabilities were. That's our joint distribution, if you like, that covers both the distribution of people testing positive and the distribution of people who do and don't have the disease. But when you look at that, you go, hold on, of people who test positive and don't have the disease, of all people, that's going to be 4.9%. And of people who test positive and do test the disease, because so many more people don't have the disease than the ones who do, that's only going to be 1.9%. So let's just look at those. Let's just condition on testing positive. So now, what's the percentage of people who test positive? Well, we can say that 4.9% of people test positive and don't have the disease. 1.9% of people test positive and have the disease, making up 6.88%. So if we now make that our denominator, the 6.88 is the number of people who test positive altogether. 4.9%, 6.88% of all people will test positive. 4.9% of people don't have the disease. That comes out to 71%. There's a 71% chance that you don't have the disease, even though it was such a good test and it's such a common disease. This cheers you up enormously. You ask the doctor to run the test again. Sure enough, you don't have the disease. That's conditional probability. Thank you for watching.